Hello, everyone. For this lecture, we're going to be talking about kinetics. It's the other topic, in addition to electrochemistry, that we needed to really cover in Chem 103. So it's great. We're getting these two topics out of the way first, and that's going to leave us more flexibility for the rest of the quarter to explore other topics that are interesting. And so today, again, it's kinetics. I'm going to be personally investigating the kinetics of consuming caffeine at 10:30 at night, and I'll get back to you on the results of that. So also, look what I just got. More markers. You see, when you get older, like approaching 40, you start getting excited about lame stuff. Just a heads up. All right, let's share the screen and dive right in. Do that. Okay. Doesn't like hotkeys. All right. Why do reactions progress? In other words, why do reactions occur? I mean, we've been talking about last quarter equilibrium and how reactions will move to the reactant or the product side based on their K, right, and their Q. And so at some point, the reaction is going to naturally go to wherever it's most stable. Okay, so whether it's going from reactants to products, or if a molecule is decomposing from a higher concentration to a lower concentration, it's going to be considered some kind of progress. Okay, and very commonly we talk about these molecules going from being electron-rich molecules to binding with molecules that don't have a lot of electrons. And so that's going to occur. And oftentimes with reactions, there's going to be some kind of hump that the reactants have to get over in order to make it to the products. And this is going to involve activation of energy, which we'll talk about more in the next lecture. But suffice it to say, kinetics involves the rate at which reactions occur. Okay. So essentially how fast they occur. And what is rate? Well, rate is simply a measurement of how certain properties of things vary over time. So when we talk about speed, we're talking about distance traveled in a given amount of time. Unemployment rate, right? That's a big one, especially right now, because before SARS-CoV-2, unemployment rate was very low. Now it is skyrocketed, unfortunately. And kind of linked with that, you can think of our wage as being a rate, right? A rate of pay. And if, some people were fortunate enough not to be furloughed or lose their job, become unemployed, there's a chance that maybe their wage was reduced as a result of this crisis we're in. And so they have a lower pay rate over a given period of time, whether that's a week or a month or salaried over the year. Okay, so that's rate, that's kinetics. What we in chemistry talk about rates, we're talking about rates of reactions. Okay, so the variation in the amount of a reactant or a product in a given amount of time. So if we go back to our generic formula, A plus B yields C plus D, we can determine the rate of any of these components by setting them equal to the change in the concentration of that reactant or product over the change in time, okay? And one thing that you got to keep in mind is that a reaction rate is always going to be positive, right? Because you can't really have a negative rate. That just doesn't compute, right? So just keep that in mind, because we'll have to change the signs to negative in some cases to account for this need to have the rate that we're solving for, be positive. Here's a very common example in chemistry. They throw out the decomposition of hydrogen peroxide. And we can say that this rate of decomposition of hydrogen peroxide into water and oxygen gas is equal to the change in concentration of the reactant over change in time, right? So the change in the concentration over the change in time. And we can write that as H2O to concentration T2 minus H2O to concentration T1 over T2 minus T1. And so one thing to point out, as with everything we've talked about, it's always going to be final minus initial. So it's going to be the final concentration after decomposition minus that initial concentration of hydrogen peroxide before decomposition, and taking that divided by the end time minus the start time, okay? You'll also notice that there's this negative sign here because the reactant is decreasing. In this case, we're looking at a reaction where something is decomposing. And when it's decomposing, it's breaking down, that means its concentration is what? Decreasing. And so if we're taking a smaller concentration here, the T2, minus a higher concentration, right? That's going to give us a negative number. And because we don't want negative numbers for our reaction rate, we put that negative sign in front of it. Okay, that's not always going to be the case. It depends on the context. Okay, so this is how we set it up. This is our equation. Let me get rid of the drawings on there. Okay. So, for example, let's look at some data, right? If we're looking at, again, hydrogen peroxide, we can see that between 0 and 6 hours, the concentration goes from 1 mole per liter down to 0.5 moles per liter. And again, they have this negative sign on there because it's going to end up being a negative 0.5 minus 1. Okay, so from 0 to 6 hours, it's going to be 1 mole per liter to 0.5 mole per liter. And then when you double that time, right, you go to 12 hours, then you're actually going to decrease the concentration by half as well. So from 1 to 0.5 to 0.25, 0.125, and 0.0625. Okay, so every 6 hours, you decrease that concentration in half. And so how would we write this? We would write this as a negative 0.5 minus 1 for this initial reaction over 6 minus 0, okay? Because again, it's the final time minus the initial time. And so if you do that and do the math, you end up with 0.0833 moles per liter per hour. And that's the rate value that they give us here, okay? And if you picked the last reaction, going from 18 hours down to 24, again, it goes from 0.125 down to 0.0625. So we would take a negative 0.0625 minus the initial concentration, in this case 0.125, all over the final time, 24 hours, minus the, in this case, initial time, 18 hours. And that gives us a 0.0104 moles per liter per hour. And here in this table, it's 0.0103, so maybe just a difference of sig figs here. And that's it. I mean, that's what we do to figure out rate in this context. So, for instance, let's say we have ammonia decomposing into nitrogen gas and hydrogen gas. How would we write this? Well, now we have a little bit of stoichiometry that we can use, that we have to use because we have coefficients here, all right? So if we wanted to look at the relationship between ammonia and nitrogen, we could write it out like this. We could say that a negative change in the moles of ammonia over the change in time multiplied by what? The molar ratio here, right? And what's the molar ratio? Well, it's 1 to 2. So 1 mole of nitrogen over 2 moles of ammonia. What does this do? This allows us to cancel out, right? We cancel our moles of ammonia, and that leaves us with our change in moles of nitrogen over time. We can further kind of condense this into looking at concentration. From that, we can extract concentration, and we can just say that a negative 1/2, because that's this ratio here, 1 over 2, times the change in the concentration of ammonia over the change in time is equal to the change in the concentration of nitrogen over delta T, okay? And then if we wanted to look at the relationship of hydrogen to nitrogen, say, we could just apply the same stoichiometric relationship, that molar ratio between hydrogen, which is, which is, there we go, which is 3, and nitrogen is 1. So it's going to be 1 over 3 times the change in concentration of hydrogen over delta T is equal to the change in concentration of nitrogen over T. Okay? So again, this is really just basic stoichiometry coming back to, relive in our psyche yet again. Let's get rid of that stuff. Okay. So let's practice. Let's try it, shall we? Let's say we have ammonia and it's going to undergo combustion and going to give, as a result, nitric acid and water. I want you to pause here and try to write the equations that relate the rates of consumption of reactants and the rates of formation of the products. While you're doing that, I'll do that, and we'll see Look, what stops here? We'll see what we come up with, okay? So here is the equation written up here. And again, all we have to do is look at these coefficients, turn them into fractions, and then set these all equal to each other relatively. So for ammonia, we could say that a negative 1/4 NH3 over delta T change in concentration is essentially equal to, right, 1/5 times delta, the change in concentration of O2 over delta T, right? And that is equal to, I think I have to make it there, right? And that's going to be equal to 1/4 delta concentration of NO over delta T. And in this case, it's not going to be negative, all right? Because this is breaking down into this, not the other way, okay? So this is being produced. So if we knew these concentrations, when we subtract it out, it won't give us a negative reaction rate. So we don't need to put the negative sign, nor do we need to do that for the water. All right, so that's equal to 1/6 concentration of water over delta T. Okay. So pretty straightforward. You just use the coefficient, make a fraction, and you'll need to know if it's negative or positive, depending on where it is. It's a reactant or product, if it's decomposing or being produced. Let's go back to slide deck and try out the next problem. So here, what we have is a graph of going back to hydrogen peroxide breaking down into water and oxygen. And this graph is plotting the concentration of hydrogen peroxide versus the time, all right? And we're starting with 1 molar solution, all right? So what this question is asking for is the instantaneous rate of production of O2 gas. Now, what an instantaneous rate is, that is really just the instant at any point where you're looking at rate relative to time, okay? And in this case, the rate at any instant happens to be the opposite of the slope of a line that happens to be tangential to this curve. All right, so this line here, and we're not going to go into that. That's calculus that you will probably come across if you haven't already. So we'll just suffice it to say that the instantaneous rate is going to be, again, equal to the opposite of the slope of this tangential line, okay? And so what they're asking for is the instantaneous rate of O2 production, given that at 11.1 hours, we have a rate of 3.20 times 10 to the negative 2 moles per liter per hour, okay? So what do we have to do here? We have to write out that expression, right? We got to set hydrogen peroxide change in that concentration over change in time equal to the change in concentration of water over the change in time equal to the change in oxygen over the change in time. Okay. And again, we have a couple things already that we know. We know that the concentration of hydrogen peroxide is 3.20 times 10 to the negative 2. So we can use that to solve for O2. Okay. Stop sharing. So we had what? Oh, oops, got me. I don't think dry erasers come out of clothing, do they? So we have 3.2 times 10 to the negative 2 moles per liter per hour. Right? That's something they gave us. And we know that essentially that is going to be equal to our negative change in concentration of H2O2 over change in time, right? Okay. And we know that the change in the concentration of H2O2 over the change in time is equal to, what? It's going to be equal to, let's go back and see what our formula is. Okay, it's 2 H2O2 yields 1 O2, essentially, right here, okay? So what that means is that that's going to be a 1-to-2 ratio, right? So what we can say is that negative 1/2 is equal to the change in concentration of O2 over change in time, right? Because again, the molar ratio between hydrogen peroxide and oxygen is 1-to-2. Okay. And this is, right, this is positive. We don't have to put a negative because it's not being decomposed, it's being produced. All right. So essentially, we know that this right here is equal to that up here, right? So we just plug that in. Negative 1/2 times 3.2 times 10 to the negative 2. That's mole. Is it moles? Yes, it's moles. Sorry. Moles per liter per hour is equal to the change in O2 times delta T. Okay. So essentially, this is going to equal this divided by 2. Okay. And so in that case, it's a negative what? 1.6 times 10 to the negative 2 moles per liter per hour. And it's going to be now, in the context of this, it's going to be positive. So it's equal to a positive 1.60 times 10 to the negative 2 moles per liter per hour. Okay. And you could do the same thing for water if you wanted to. The ratio is different here, so you have to keep that in mind. It would essentially be 2 to 2 or 1, right? So, okay. So what changes? What determines the change in the rates of these reactions? Well, there are a number of different things that change. For one, the chemical nature. So what the reactants and products are made of, right? Certain elements and molecules are going to behave differently when exposed to the same things, right? If you take two metals, I think the example they use in the book is sodium and iron, right? They're both metals. If you set them out and let them react with the air, overnight, the sodium is going to completely react. Okay, whereas the iron will be essentially unaffected, right? Over time, if there's water involved, as we learned last week, it will eventually oxidize and corrode, right? But not nearly as quickly as sodium reacts, right? And again, kinetics is measuring this rate and change over time, right? So what the chemicals are made of is going to determine the rate. Some things react very slowly. Some things explosively react, right? So quickly that it explodes. Another thing is going to be the physical state. So solid, liquid, gas, and then how, for instance, if it's a solid, how it's broken up. If it's a solid chunk versus if it's a lot of different pieces, right? If you chop up something into smaller pieces, you're increasing the surface area. And in doing so, you end up allowing whatever it's reacting with to cover more of that surface and speed up the reaction. Okay. So let's say you are wanting to start a campfire. You don't just light a log on fire, right? That would take a really long time to catch on fire. The rate of reaction is slow. However, what do? You get kindling, you get small pieces of wood, and you light those on fire because that that reaction rate is much more quicker. Much more quicker. It's quicker, okay? So so the state that it's in, whether it's solid, liquid, gas, or the type of condition of that state affects the rate. And temperature. I mean, we all know the temperature affects the rate of things, right? We know that because we do it all the time in chemistry. We heat things up to speed up the reaction rate. So that is pretty, that should be hopefully common knowledge. And then of course concentration. So generally speaking, the more concentrated the reactants are, the rate is going to increase with that. Okay, so the higher the concentration, the faster the rate of reaction. Okay, there's just more of it available to react, so it's going to react more quickly. When we think of like pollution, again, the higher the pollution, the higher the more quickly things are going to react. So if we have a lot of sulfur dioxide in the environment, that's going to react and we're going to get acid rain, right? And that's going to then break down things like calcium carbonate in our statues and edifices and things like that. So so the concentration affects the rate of reaction. And then finally, the presence of catalysts, right? And we hopefully know that because we've been told from very early on that what is a catalyst? It's something that quickens the rate of a reaction without changing itself, right? And so here's again another plot, and this is looking at the difference in the amount of energy needed if you don't have a catalyst. So the uncatalyzed reaction, it's going to take more energy to get over that hump and form the products than if you have a catalyst, right? It's going to speed it down. And for instance, you take, say you cut your finger and you want to disinfect it, because it's okay to disinfect your finger. You don't want to disinfect your lungs, in case you didn't know that. I know all of you guys know that because you're all brighter than some people in positions of power right now. But let's say you want to disinfect your finger. You take some hydrogen peroxide and you pour it on that cut. Now, you're not supposed to use hydrogen peroxide after that, initial disinfection, because really it can prevent your skin from healing. So use it initially and then cut it out. What happens? You get these bubbles, right? You get this foamy bubbling going on at the cut. What's happening? It's just interacting with enzymes in your tissue, right, in that wound, which is speeding up the rate at which hydrogen peroxide decomposes into water and oxygen. And the bubbling is the oxygen being released, right? So it's these enzymes that are catalysts speeding up that decomposition of hydrogen peroxide. Whereas if you just poured that into a little shot glass and just watched it, it's not going to bubble, right? It's going to decompose, but it's going to take a lot longer because there are no enzymes in there to speed up the reaction. Other factors that determine the rate of reactions. Well, a rate limiting step, okay? This is whatever step is slowest in that reaction, okay? So kind of like limiting reagents, right? A reaction can only occur as long as the limiting reagent is still around. Likewise, reaction rates can only happen as quickly as the slowest step in the reaction, right? And we use this rate limiting step to determine what we call the rate law, okay? So this is saying that the rate of a reaction is equal to K. K is going to be again, a constant. That's our rate constant, times the concentration of however many reactants and products we have. Okay, so A, B, C, etc. And then the exponents are going to be, these have to be derived experimentally. So the K has to be derived experimentally. The exponents need to be derived experimentally, but essentially what those exponents are the effects of the reactant concentrations on that reaction rate, okay? And that effect on the rate is going to be considered a reaction order. So first order, or second order, or zero order. If that concentration doesn't have an effect on the rate, then it's going to be zero, okay? And so you have to determine what those exponents are by looking at experimental validations So different trials, and then seeing the relationship of the concentrations of your products and reactants. And that's what we're going to learn today in the rest of this lecture. Okay, how to determine K, how to determine exponents. These exponents are not the coefficients, okay, like we used in equilibrium. These are not coefficients of reactants and products. Rate law, reaction order. So again, exponents determine the reaction order. Let's say that the reaction exponent for A is 1. Let's get to my annotate, okay? Let's change my color. Okay, so we're saying that M is equal to 1. That means that the reaction is a first order with respect to A. So A, not the overall reaction, but just A. A is first order. If M is 2, then it's a second order, okay? And same applies for these other ones, right? If N is 1, then B is first order. If N is 2, then B is a second order. If either of these are 0, then the reaction is a 0 order, okay, for A or B. And what that means is that the concentrations of those reactants have no effect on the rate of the reaction. And then to now figure out the overall reaction order, so everything, we just take the sum of these orders of the reactants and add them, well, the sum, right? So if M and N are both 1, then it's going to be M plus N, or 1 plus 1, and that's 2. So the overall reaction order is 2. All right, so here we have an experiment, and they say that the reaction of nitrogen dioxide with carbon monoxide gives us a second order for nitrogen dioxide and a 0 order for carbon monoxide. What is the rate law of the reaction? Okay, well, that is just saying that rate, right, is equal to K, and then we have nitrogen dioxide. I said it was a second order reaction, so 2 times the concentration of carbon monoxide, and they said that that was a 0 order reaction. And if that's a 0 order reaction, that means that it has no effect. And so we can really just get rid of it and say that rate is equal to K times nitrogen dioxide. There. Okay. Pretty straightforward. What about this? Okay. Ozone in the upper atmosphere is depleted when it reacts with nitrogen oxides. The rates of reactions of nitrogen oxides with ozone are important factors in deciding how significant these reactions are in the formation of the ozone hole over Antarctica. And I kid you not, I was working on this presentation today, and I noticed in the news on CNN that they had just discovered the largest ever Arctic ozone hole that developed this spring, and now it's closed. And so here's, if you're interested, maybe you've already come across it, but here's a link to it if you want to see it. Essentially, spring was what, like a month ago. So it was discovered less than a month ago as being the largest ozone hole ever, and now it's completely closed. Interesting. So I thought that was pretty cool. Things happening in real time. Let's take a look at that. Let's see, how that could be. Does that make sense? That's a pretty fast patch in the hole. So here is the formula for what's going on, and here are the different measurements of nitric oxide and ozone, and then giving us the these concentrations. So what they want to know, what they're asking for, is what is the rate law and the rate constant for the reaction? So what's K, and how do we figure out what those exponents are going to be? So I'm going to, you can pause it and see if you can work this out, see if you know enough to get through it. If not, just hang tight. I'm going to write a little bit on the board and then come back. Okay, so I've written the rate law incomplete in this form. We say rate is equal to K times nitric oxide to the M times O3 to the N. And to start, breaking through, before we can solve for the rate, we have to know what those exponents are. And to do that, we have to keep in mind what I said these exponents represent. They reflect the effect of the reactant's concentration on the rate. So what we want to do is we want to look at that data table and see instances where these concentrations for these particular reactants change, fluctuate, and the other reactant stays the same. Okay, because if the other reactant is also changing, then it's much harder to see how that affects the rate. But if you can find a trial where, or you can find several trials where one thing is changing and one thing isn't, and you can see what value is for the rate and how that is different based on the change of this concentration. All right, so let's look at that table again. All right, so what we have to do is we have to interrogate this and see in which of these trials is the concentration of nitric oxide staying the same and ozone changing. Well, looks like in the first three, this is constant. Nitric oxide is constant, and in the first three, it's the ozone that's changing. So if we're wanting to find what M is, what the exponent or the order for nitric oxide is, we've got to go to these next three trials where the concentration is changing for nitric oxide. And so what do we see? When nitric oxide goes from 1 times 10 to the negative 6 to 2 times 10 to the negative 6, or effectively doubles, the ozone stays the same, which is good. So that means it's not changing, so it's not going to have an effect on that rate just yet. And what's happening to the rate? Well, the rate also is doubling from 1.98 times 10 to the negative 4 to 3.96. Okay. What happens when we go, say, from trial 3 to trial 5? It goes from 1.00 times 10 to the negative 6 to 3.00 times 10 to the negative 6. So it's tripled its concentration. And likewise, the rate is tripling from 1.98 times 10 to the negative 4 to 5.94 times 10 to the negative 4. And so what does that mean? That means there is a direct proportionality between the concentration of nitric oxide and the rate, right? It's 1-to-1. When the concentration of nitric oxide triples, the rate triples. So we can easily say that NO is going to be a first order reaction. Okay. So now let's figure out what ozone is. Let's go back to that table. And as I said previously, the first 3 trials have a change in ozone, but no change in nitric oxide. And what's happening with the concentration of ozone? Well, if we look at the difference between trial 1 and 2, we see that the rate doubles from 3 times 10 to the negative 6 to 6 times 10 to the negative 6. And when that happens, what's going on here? We have this so the rate is going from 6.60 times 10 to the negative 5 to 1.32 times 10 to the negative 4. So that looks like that's also I would say that's doubling, okay? And then if we look at between trial 1 and 3, that's tripling from 3 times 10 to the negative 6 to 9 times 10 to the negative 6. And yeah, 6.60 times 10 to the negative 5. If we tripled that, I think that should be 1.98 times 10 to the negative 4. So it's tripling. So it looks like it's a 1-to-1 reaction as well. So then we can make our N equal to 1. Okay. So now all we have to do is plug in those concentrations, and we can then solve for K. So let's go back and share again, and let's pick some concentrations. We could say that, let's just look at the first one, right? We have rate being 6.6. I'm going to write this down. 6.60 times 10 to the negative 5. That's our rate. And for that, we have a concentration of 1.00 times 10 to the negative 6 for nitric oxide, and 3.00 times 10 to the negative 6 for ozone. Okay. So if now we've solved for our exponents, the other step in that question was to solve for K. We could say that let me move over here. We could say that K is equal to 6.60 times 10 to the negative 5 over 1.00 times 10 to the negative 6 to the first power. That's the concentration of nitric oxide, times 3.00 times 10 to the negative 6, also to the to the first power. And I'm going to pause it just a second. I'm going to do this on my calculator so you're not sitting here watching me fumble on the keys. Okay, so if you compute this all out, you should get 2.20 times 10 to the 7th liters per mole per second. All right, that is a big number, right? 2.2 times 10 to the 7th. So that hopefully makes sense that the ozone hole that was the largest ever recorded a month ago has now healed itself and has patched itself up in such a quick period of time because the rate is such a high number. That's a fast reaction. So it makes sense that in this case, in the CNN article, that it did happen. And if you read the article, it wasn't necessarily attributed to the COVID-19 crisis, but rather these vortex winds, these polar vortices, and so bringing in compounds and molecules to react with the ozone to patch it up. Gotta love it when real world examples happen to simultaneously occur when you're learning stuff, right? Okay, so that was that one. Here is really pretty much the same thing, only in this case, you're using the initial rates and, the experimental data down here to determine the rate law and not only the rate law, but the rate constant. Okay, so in this case, you have to look at essentially the relationship between the different examples, the different rates in these data, and the different concentrations. Okay, and set up a ratio to each other. So the rate of, say, trial 1 over the rate of trial 2, or opposite, depending on, again, when these things are constant and when they change. Okay, so pause it here, see what you can come up with, and I'll see you in just a few. Okay, so we're basically solving the same kind of problem in this example, only we're going to use a slightly different approach in case it's not so obvious the relationship. So in that previous problem, I just kind of looked at how things changed from one trial to the next, and it was a real clean one-to-one, or the concentration doubled, and as a result, the rate doubled accordingly, and they were both first order. It was pretty simple. When you have data that isn't that obvious just by eyeballing it, you can set it up pretty easily as a ratio of one trial to another trial. And so in this case, to solve for M, we need to look at trials where the M concentration is changing, but the N concentration is not changing. Okay, so if we go back to that table here, the M concentration changes from 0.1 to 0.15 between trials 1 and 3 and 2 and 3. So in this case, we've got to use this third trial because that's where it's changing. And where's a scenario where the N concentration is not changing? Well, between 1 and 3, right? It changes in the second trial, but in trial 1, it's 0.1. In trial 3, it goes down, it goes up to 0.15 and then back down to 0.1. So it's not changing. So if we use trials 3 and trials 1, we'll get a scenario where the concentration of that M exponent, or for nitric oxide, it changes, but for chlorine, it doesn't. And so we just plug in our rates, plug in our concentrations, and I'll show you what we can do from there. Okay, that's what I've done. I've taken rate 3, and I've written down what the value is for the rate of trial 3, not rate 3, and the rate of trial 1. I've written the value there as a ratio to each other. And if we write that, we say that's equal to K times 0.15 M times 0.10 N over K times 0.10 M times 0.10 N. Okay, so really all I've done is I've written a rate expression for the third trial. If you looked at everything on the numerator, that would be the rate expression. And then if you looked at everything on the denominator, that's the rate expression for the first trial. And I just put them on top of each other. Okay, and why do I do that? Because in this case, something cancels. All right, what cancels? Well, this 0.10 to the N. Okay, and so what we end up getting is, let's do blue. Move back over here so I'm not blocking the light. We get a 0.00675 over 0.00300 equals K also cancels, right? It's K over K, 1. Okay, so you can kind of see that. So K cancels, and so we end up with just 0.15 M over 0.10 M. Okay, so 0.15 divided by 0.10, that's going to be 1.5 M. And 0.00675 divided by 0.00300 is 2.25. And so now, to solve for N, we can do natural log. Remember natural log when we were using it in pH, right? We could use the natural log to solve for pH. We can also use the natural log to get this exponent M by itself. Okay, so if we apply the natural log to both sides, so the natural log of, something's going off, I wonder what's happening. Calendar update. Natural log of 2.25 equal to the natural log of 1.5 to the M. That essentially makes this, that flips this, right? So it makes this natural log of M times 1.5. Okay, so to get M, oh wait, I'm sorry. That's flips it to M times the natural log of 1.5. There we go. Okay, so to get m by itself, we just divide each side by the natural log of 1.5. Natural log of 1.5. Okay. Cancels that. And so m equals the natural log of 2.25 divided by the natural log of 1.5. And that should equal 2. Okay. Make sure you do this on your calculator to make sure that you're plugging this in right and that you get 2. So what is 2? 2 is m. So that means that what was that? Nitric oxide is a second order reaction because it has a 2. So we've got the 2 for m. I'm going to write that. I'm going to erase all this now. Say that m equals 2. And now we just do the same thing for the n. Okay, we have to look at the trials that have n, or the chlorine, changing, but the nitric oxide, or the m, not changing. In that case, it's reaction trial 1 and 2, right? In 1, it goes from a concentration of 0.1 to 0.15, whereas the nitric oxide stays the same. Okay, so we can write that as essentially trial 2 over trial 1. So trial 2 is, oh, let me get my color here. Okay. The rate is 0.00450 for trial 2, and the rate for trial 1 is 0.00300, right? And that is equal to K times, what's the concentration of trial 2 for the nitric oxide? It is trial 2, it's 0.1, 0.10 to the m, times, what's the concentration in trial 2 of chlorine? It's 0.15 to the n. Okay. And then what's the concentration in trial 1? It's 0.10, so K times 0.10 times 0.10, the concentration of chlorine. All right, so that's what I've written up here. Again, I'm just taking the rate law of one trial and putting it over the rate law of another trial, okay? And what happens is, in this case, K's cancel out, and this 0.10 m cancels out, and I get 0.00450 over 0.00300 is equal to 0.15 n over 0.10 n. Okay. And so in this case, 0.00450 divided by 0.00300 is 1.5. And this, we already did that. That's 1.5 n. And so because it's 1.5 is equal to 1.5n, that is simply a 1-to-1 ratio, right? So n must be equal to 1, right up here. N equals 1, right? So I'm going to erase this, and now we can just plug those values in for any trial to solve for K. Right? It shouldn't matter which trial we pick. If we take the values for, let's see here, go back, see what we got. Uh-oh, what happened? Back to meeting. Oh. Sorry, bear with me. Is this it? No, that's not it. What happened to my, there we go. All right, so let's just use trial 1. We can say that, let's use blue, 0.00300 moles Lear -1 equals K times, what's nitric oxide? 0.10 to the 2 times chlorine is 0, also 0.10 only to the 1. Okay, stop share. Okay, so I've just written out the rate. This is the rate law, right? Using the rate value for trial 1, the concentrations of trial 1 raised to their power 2, because m is equal to 2, and 1, because n is equal to 1. And to solve for k, we just get k by itself, so that's 0.00300. Right? And if you do the math for all that, it should be 3.0 mole -2 seconds 1 is equal to K. All right. And so now we have our K and we have our exponents, and that problem is solved. One last reaction, and it's the same thing, only again, I want to give you yet another way to be able to look at these relationships in these different trials. This is looking at nitrogen dioxide and carbon monoxide as the reactants, forming nitric oxide and carbon dioxide. And so they've taken several different measurements here. I guess there are 4 trials, if you will, and they want you to look at they want you to solve the rate law. So essentially, solving the rate law is setting up the rate law expression and finding the values of these coefficients. and then solving for K, okay? And so pause this, see if you can come up with an answer. Again, it's just applying the same things that we've applied before, where we look, where do the concentrations remain constant, right? So it looks like trial 2 and trial 3 stays the same for nitrogen dioxide, and trial 1, 2, and 4 concentration stays the same for carbon monoxide. So use those in a way to set up your relationship, see if you can solve. Alrighty, so I've written the rate law up here incomplete because we need to solve for the exponents and for K. And I've written this out, these concentrations and these different trials, as yet another approach that you can take if the other two techniques don't make as much sense. You can think of it as, here's the concentration of the first reactant, nitrogen dioxide, here's the concentration of the second reactant, carbon monoxide, and here are the initial rates for each trial. And you can write them, in a linear fashion and just see what's happening at each step. So in the first trial, we go from nitrogen dioxide concentration of 0.1 to 0.2. So what has that done? That has doubled, right? In carbon monoxide, it goes from 0.1 to 0.1. So it's the same, or, it's remained constant. And what has the rate done? The rate has quadrupled from 0.0021 to 0.0082, okay? Roughly quadrupled. All right. And then going from the second trial to the third trial, we have 0.2, 0 there, 1, kind of losing my sig figs here. No sense to do that. We go from 0.2 to 0.2, so that's constant. All right, and here from a 0.1 to a 0.2. So in this case, this one is doubling. And then for the last one, it's and then what happens with our rate? Our rate is 0.0082 to 0.0083. So essentially stays the same, right? Times 1, or constant. And then the last change, we go from 0.2 to 0.4. So that is again going to double. 0.2 to 0.1, that goes down. So that's reduced in half. And the reaction goes from 0.0083 to 0.033. So that's, again, quadrupled. So what does this mean? What is the relationship of nitrogen dioxide to the rate? Well, as you can see, in the first trial, when this doubles, this quadruples, right? So that's a factor of 2. And our carbon monoxide remains constant, okay? So again, you want to pick something where your concentrations for one reactant changes and the other one remains the same. So we can say that the M for nitrogen dioxide is 2, right? Because it does the same thing down here as well, right? This doubles, this quadruples, and this goes down. So, I mean, that's definitely not going to affect things. So overall, we can say M is equal to 2. Now for N, there isn't any situation where this changes and this remains constant. And as a result, the rate changes, right? Between this step here, it stays the same. When our NO2 is constant and not changing, right? Between reactions 2 and 3, it stays constant. However, the carbon monoxide is changing, yet we get no change in our rate. Well, that means this has no effect on the rate. So what does that mean? That means that it must be a zero order, right? Remember, when something has a zero order, that means the effect of its concentration has no change on the rate. And that's clearly what we see here. So now we have more of our rate law. All we have to do is plug in some numbers and solve for K, right? So we could plug in really just, let's just do trial 1, right? These right here. See what we come up with. We know that K is equal to the rate over concentration of NO2 to the second power, right? Because carbon monoxide has a zero order, so we just don't include it in our expression. And so that's simply 0.0021 over 0.10 squared. And of course, our units. And this is moles. Okay. And if we do this math, we get K equals 0. Right, just well, this is squared, so yeah, that's going to be 0.21, I believe. Moles, -1, seconds, -1. Okay, there you have it. 3 different ways to solve the same type of problem. 1, just eyeballing it. 2, doing a ratio of one trial over the other. And then 3, making connections to each trial and then seeing whether they're doubling, staying the same, quadrupling, and so forth. Okay. There will be an ICA on kinetics on Thursday, so there'll be more opportunity to practice these kinds of problems. I'm sure the homework will have some of these problems too. All right, that's it for today. So see you next time.